Okay, you guys, are you ready for this? Everything that we have learned about electric forces and fields and magnetic forces and fields are all coming together here in electromagnetic induction. So this is the end all, the be all, well, not of all of magnetism and electricity, but for physics 30 it is, and that is electromagnetic induction. So we already heard about this guy Ørsted, right? He's the guy that figured out, oh, if I have an electric current running through a wire, then it's going to produce a magnetic field going around it, right? So these guys named Faraday and Henry, they figured, well, does the opposite still ring true? What if I have a magnetic field? Could that produce an electric current in a conductor? The answer is yes, but with conditions. So with an electromagnetic induction, it produces an induced voltage in a conductor using a magnetic field, but if it's just a steady magnetic field, there's no current. So that's not what produces an electric field. A changing magnetic field will produce a current and therefore an electric field. Okay, so it doesn't matter if the magnet moves or the wire moves, as long as there's relative motion between the two. As long as you have a wire moving around a magnet or a magnet moving around a wire, you will have a current being induced. So a couple of the methods that we will go over in our Physics 30 class here is, well, the first one is moving a magnet through a solenoid. So if I have a magnet here and I have a solenoid, which is of course a coil of wires, which we know itself already can induce a magnetic field, but now we're turning it off, okay? There is no current going through here. G down here means galvanometer. That's something that just measures current, so it's not hooked up to a power source whatsoever. There's no way for current to move here through here due to electrons traveling unless we move this magnet, okay? So if this magnet is stationary here and then I move it towards the solenoid, a current will be induced in this solenoid. If I have it here and I move it away, a current will be induced, but guess what? In the opposite direction. So as long as there is some movement of the magnet with respect to the coil, there will be a current. Another situation we're going to go over is if we move a conducting rod through a nice, steady magnetic field. So in this case, the rod is the thing that's moving, the conductor is, but the magnetic field is steady. So it's opposite of what we just had, where we had a magnetic field that we moved back and forth with respect to the solenoid. So here I have the possibility for a current to be set up, right? To go here through the conducting rod down through this circuit, right? And this is just through a resistor, which we're not going to learn about in Physics 30. So if I have this nice steady magnetic field here, it's going into the page, and then I take this rod and I move it back and forth along here, since it's all connected by a conductor, that is going to conduct electricity, okay? So then the electrons will be moving then through here. The cool thing about this is that since it's moving back and forth, the electrons aren't just going to go one way. They're going to go back and forth and back and forth and back and forth, because if I move it this way, they're going to move in one direction. If I move it this way, they're going to move in a completely different direction. And we will get to how we figure those directions out in a minute. Finally, something we'll go over really quick, and this is a way that electromagnetic induction is used, is in a transformer. So these are used everywhere, obviously. You see power lines going through your cities. And then you often see off the highway much bigger power lines, and that's because they go to a place that's called a transformer, a step-up transformer, so then they can carry more current when they're not in populated places and less current when the power lines aren't in populated places, and that's because of a transformer. So here I have what's called a step-up transformer. That's because I have more coils on this side than I do on this side. So if I have this switch closed, I have a DC source, so that's direct current source, meaning the electrons are just going to flow from the negative terminal to the positive terminal. They're just going to keep going like that. Okay? And if I close the switch, then it's just going to keep doing that. Nothing's going to happen over here, because obviously if this is a soft iron core, it's something that's very magnetic. But if I just have direct current and there's no movement with regard to the current and the magnet, then nothing's going to happen. So I put the direct current on, and then I take the switch and I turn it off and on and off and on and off and on and off and on. What happens is you have that changing magnetic field then, which is then going to induce a current in this solenoid. And because there's more coils, it's going to induce a greater current. And then we have a galvanometer over here that can measure the current, which will in fact be more than this current, okay? So with electromagnetic induction, we get alternating current, which is really, really important. Direct current is really just moving electrons from the negative to the positive, okay? And once all the electrons are moved to the positive terminal, that battery's either dead or needs to be recharged. So that's how it works in our phones. When it's being recharged, what it's doing is it's taking the electrons and putting it back on the negative terminal. The only problem with that is you can never fully recharge, and that's why things like your phone, which you have to recharge the battery all the time, will lose charge over time. Its battery life will be less and less and less because we can never fully restore that. That is why alternating current is so fantastic, because we don't have to rely on batteries just to move electrons to one terminal all the time. The electrons are going back and forth and back and forth and back and forth, and that is still creating a current. All we need is electrons to move. They don't need to move from one terminal to another. They just need to move back and forth in order to create a current. So this is what electromagnetic induction helps us with, because of course we have very back and forth nature here. Just one note about the transformer. So this is what we call a step-up transformer, okay? So when we have a smaller number of coils to a larger number of coils, that's a step-up transformer. Okay? And then the other way, if we go from, say we switch, we put the DC source over here and then switch over here and the galvanometer over here, that would be a step down transformer, which is what needs to happen from power lines that are not in populated areas into populated areas. They need to step down that transformer. They need to step down the current so it's not as high in populated areas. All right, so let's really investigate this and how this works and how which way the electrons and the current are going to flow if we move a magnet with respect to a solenoid. All right, so we know which way that electrons or current is going to move because of Lenz's law. This is really, really important. It's not like Lenz like you look through, it's Lenz like this is the guy's name that figured this out. So it's really, really important to note, okay? So what does it say? It says, induced current flows in the direction which produces a magnetic force, blah, 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 that opposes direction. That's so, so important. Opposes direction of applied force. So what does that mean? It means that nature does not like change, okay? Think of nature as a crotchety old man who never wants anything to change. So say I move a magnet near to a solenoid. That solenoid is freaking the heck out because its nature was to have a magnetic field not that close to it. So you bring a magnetic field close to a solenoid, it's gonna freak out and try to push it back the other way. It's going, I don't know you. Go back to where you came from. So like I said, it's a crotchety old man who doesn't want any change whatsoever. But the thing is, once that solenoid kind of gets used to the magnet being there, the magnet stops moving, but it doesn't move away, then the solenoid like gets used to it, and then you try to bring the magnet away and the solenoid's like, no, I just got used to you, come back here. Okay, that's all Lenz's law is it's saying that nature really likes being in the state that it's already in. It doesn't like change, it doesn't want to change, so it's going to oppose that change. And then once it gets used to that change, it's going to oppose the change from before that it wanted. So nature is just a finicky old beast, but that's how it works. So Lenz's law, it's going to induce a current that flows in a direction that's going to produce a magnetic force that opposes the direction of the applied force. Okay, what the heck does that mean? Let's go over an example. Oh, I pretty much just said all this. So there you go. You can write it down if you need to. So if I want to figure out the direction of the current induced in a solenoid to either push a magnet away or to pull it back, first we have to consider the direction of the magnet. So that's the direction of the work being done. Is the magnet being moved towards or away? And of course, remember, nature wants to do the opposite of that. So then the polarity of the coil necessary to oppose the magnet's motion, meaning we know that if we have a solenoid that produces an electric field, it's going to produce a magnetic field with our thumb pointing at the North Pole. So you just basically have to figure out which side of the solenoid needs to be the North Pole and either repel the magnet or attract the magnet. And then of course we're going to use the direction of the current or the electron flow with our left and right hands. So for example, I want to determine the direction of current flow, not electron flow. We're determining the direction of current flow here. So the motion of the magnet is going towards the solenoid. So what's going to happen? What should the opposing force be? Well, again, this crotchety old man here is like, no, I don't know you. Go back to where you came from. So it's going to try to oppose that motion. Okay? So how is this going to oppose the force? What polarity, which side would need to be the North Pole and South Pole of this solenoid in order to oppose the force? Well, we know that like poles repel, so therefore the solenoid is going to induce a current so that that is now the south side and this is now the north. Because again, if this is south and we're moving the South Pole towards the solenoid, having a South Pole here will create that opposing force pushing it back the other way. So now we have to figure out which way the current is going to go in this. So current, we're talking about current flow, so that's our right hand. So we always point our thumb towards the North Pole. So there's our thumb going like that. And then as we can see, our fingers are going under and over. Okay, which I know it's not always easy, but look at which side do you think is going under and over. Well, this dotted line means behind and this solid line means in front. So it looks like this is the under and over that we're looking at here. So it kind of looks like my current is going under and back here and then coming out and going over here. Okay, so that's what's happening with my current. So what's happening with my current? It's going this way around. So it's going to keep going under and over. And here it's going down in the front sides of the coil, under and over, down here. And going to go this way. So the galvanometer has a little thingy. What do you call that thing? I don't even know right now. It has a little hand that moves in the direction of the current. So the galvanometer is going to point this way because this is the way that the current is going. Okay, so that's what we're doing with Lenz's law. We're just trying to figure out which would the opposing force be. Okay, so here we're moving towards, so it's going to try to oppose it in the other direction. Since I'm moving a South Pole towards it, it's going to create a South Pole there to try and get it to go away, basically. Okay, but as I said before, once the solenoid gets used to having the south pole near it, as soon as you move it away, it's gonna go, hey, I just got used to you. Can you come back here, please? Like, we were just starting to get along, everything was going well, and it's actually kind of mourning the loss of this magnet. So it's going to try and pull it back towards it. If I can get the right pen here. It's gonna try to pull it back towards it this way. So in this case, the opposing force is going, no, come back here. So again, what needs to happen to the polarity of the solenoid in order to produce this opposing force to say, hey, come back here? Well, again, we know that unlike poles repel. So if I have a north pole right here, that's going to pull it back because that's going to attract this south pole. Okay, so there we go. That's going to be my south pole. So now if I'm looking at which way the electron flow, nope, we're doing current. Which way the current is going to go, I need to use my right hand. And now my thumb is pointing towards the left here because now the north pole is going to be on the left. What's going on? It's going up and over like that. That's what my hand is doing, going up and over. So that's what's going on with the current here. Now it's going in the opposite direction. It's going to go up here and over here and behind like that. And it's going to go up and over. So it's really going up through the fronts of the coils here. And that's going to go up and over here. It's going to go down, keep going down there. And here we can see it's actually going to the left through the galvanometer. Okay, so this is the way our current is heading in this situation. Okay, so you ready to try some more examples? Let's do one more. So this one's a little bit different. This one we're actually going to move the coil. And so now the coil is going to be really, really confused because we're moving it, but it's going to like still try to oppose that motion and say, no, I was good over there. Can you please keep me over there, right? Because it's moving towards this magnet. So the magnet, again, is doing nothing. It's all about what's happening inside the solenoid, okay? So if we have the motion of coil towards the magnet, of course, our opposing force is going to try to get it away from that magnet. So our opposing force is going to the right. So what needs to happen in order to oppose it and to try to bring it back this way? Well, in this case, we're moving them together. It's trying to repel. So it's going to create a north pole here and a south pole here to try and oppose those north poles, right? It's moving towards the magnet. It doesn't want to. It wants to move back away from the magnet. How do you do that? You oppose with like poles. Okay. So we're going to use our right hand rule because it didn't say current or not, but I'm assuming we're still going off of the first example and that's at current. So let's still use our right hand. Okay, so again, north pole on the left, fingers are going up and over. So up and over and up and over. So it's going up here, over like that, down behind, and then up in front. Okay, and then over, down behind, down here, and we have another current going to the left. Okay, so it doesn't matter if it's the coil that's moving, it doesn't matter if the magnet is moving, it's just always going to try and oppose that force, okay? So just to give you guys a little bit of exposure to this same scenario, but in a situation that looks a little bit different. And again, I'm sorry about the printer here. It just did not print it off very well. So hopefully you can see this all right. But this is a release diploma item. And so this is still the same thing, but people just see a copper ring and think that that's not a solenoid, so I don't have to think about it in that same way. But yes, you do. It's going to react the exact same way. As long as you have a conductor in a circle, it's going to act that way. So we have a very strong bar magnet dropped onto a foam block through a copper ring that has a slit cut into it as shown below. So the slit is there just so then the electrons can't fully go around, so they're going to collect at either X and Y, okay? So the question does in fact ask, I'm not going to show you right now, but it says, when the south pole of the magnet moves into the ring from above, the direction of the electrons inside the copper ring will move from which X to Y or Y to X. So that's what we want to figure out first. So again, what do we know here? We know that this is moving towards the copper coil, which is going to be acting as a solenoid. So it's going to try and oppose that motion and push it back up. So I know that in order to oppose this motion, it needs to create a magnetic field that opposes this magnet. So that's going to now be a south pole, and this is going to be the north pole, right? Because those like poles will repel each other. Okay, I want to know which way the electrons are moving, so I'm using my left hand here. My thumb is going to point to the north pole. So look at that. That means that my fingers are curling over here from Y over to X. So my electrons here are moving away from Y and towards X. Okay, so that's the first part of the question. We know that it's going to go from Y to X. And then we want to know, compared to X, the nature of the charge on Y. Well, what's going to happen here? The electrons are moving around and they're just going to be gathering here at X. So what does that leave Y? That leaves Y as positive because, of course, all the negative charges are going to move here and gather up here, and then that's leaving this guy more positive. Okay, so that's a similar question, but just in a slightly different situation. Yet another situation in which we can apply pretty much everything that we learned in electric forces and fields and magnetic forces and fields. So here we have a positively charged sphere right there. It's in between these two plates, but it's on an insulated string, meaning that no charge can move up the insulated string. Okay, we have two vertical metal parallel plates that are connected to a coil of wire. Doesn't that look fun? A magnet is suddenly thrust into the coil of wire as illustrated below. Okay, so we have to figure out what the heck is going to go on. It's basically, the question is, when the magnet's moved as illustrated above, then the direction of the motion of the positively charged sphere is going to be what? Towards plate 2 or plate 1. So first off, we know that this positive sphere is going to move towards whatever plate becomes negative. Okay? So what we really want to know is, where are the electrons moving? Are the electrons going to move towards plate 1, or are the electrons going to move towards plate 2? That's what we want to know. And I know that's like a question where if I was just to ask that, you guys would know it, but now it's in this huge scenario. It's kind of intimidating. It's like, what the heck? So let's really look at this. So we know, first of all, if we move the magnet towards the solenoid, what's the solenoid going to try to do? It's going to push it back the other way. It's going to get out of here. I don't like you. I don't know you. This was not an agreed upon invasion, so let's just get you away from me here. So we know that's going to be our south pole, that's going to be our north pole, because again, like poles repel, so it's going to try to repel there. So here, again, I just care about what's going on with my electrons, so I need to use my left hand because I want to know which way are the electrons going. Are they going to go towards that plate, or are they going to go towards that plate? Because that's going to tell me which way that my positive sphere here is going to move, right? So, north on the right. Point the thumb to the right. Fingers are going up and over. So this is a little bit more difficult to really figure out what's happening here. Up and over and under, kind of like that. So again, just really take a look at it and see what would happen there. If you need to kind of look with your right hand and say and figure out which of the plates would be positive, you could do that as well, because with the right hand it's going under and up like that. So it looks like with the right hand it's going up behind, okay, meaning it would probably be going up towards there. So that means our electrons are probably moving up in front, down behind, meaning down this way and over to here. okay? So it might take you a few minutes to really just look at that, but if you look at it for long enough, you notice, oh, the electrons are going up here and they're going behind. So if they're going up and behind and up and behind and up and behind and up and behind, eventually they're going to go up this one and behind it, and then there's no more coil and it's going to go towards there. Okay, so that is the direction that my electrons are moving. So if my electrons are moving over here towards this plate, guess what its charge is going to be? Negative. This guy is going to have that positive charge. So guess which way the positive charge is going to move? It's going to move towards that negative plate right there. Okay, so it's going to move towards plate 2. Okay, so that was just one of the scenarios. We still have the scenario of the conducting rod moving through a magnetic field. So let's go over that one. So if we have a wire moving through a field, we know the current's induced, okay? So the field surrounding the wire is gonna oppose that pre-existing field. And that's all we gotta know. So again, easier if I just kind of show you how to do an example. So what we're gonna do, in this one we're using our third hand rule because we have an external magnetic field, we have a force, and we have a current, okay? So that's our third hand rule. So your palm has to just oppose the direction of applied force. So if the rod is being forced to the right, the magnetic force is gonna go to the left to try and oppose it, okay? So of course our fingers are still the direction of the pre-existing magnetic field. Into the page, out of the page, left, right, north, south, just like that. Thumb is still the direction of the induced current flow. Now, an important note. Induced current. So far, anytime we've seen the word current, we have immediately thought right hand, right? Unfortunately, that's not the case anymore. I'm sorry, I don't make these decisions. These were just made for me. Anytime you see that extra word induced there, that actually is asking for electron flow. And therefore, you need to use your left hand. Because it's really important to note that electrons are the current. They are the thing that's flowing. We don't have a bunch of protons flowing, right? Because we know they can't be disconnected from their nucleus. But current was thought of before we actually knew it was the electrons that are moving, and they just happened to define it in the opposite direction. And it still is important to use in some higher physical situations and in some electrical engineering. So that's why it's still around. It's still not completely discounted. But really what is moving is the electrons. They are going around the circuit, okay? So when I'm talking about induced current, what's really moving, what are we actually making move by moving the rod is the electrons, okay? So just current means right hand. Induced current means left hand. I'm sorry. Okay, so I'm just going to do one example here. Well, no, never mind. There's 2 on the page. 2 examples. I take it back. And then I promise I'm done because I think this video is probably long enough. It's, I think, the longest one I've ever made. But hey, this is a pretty big topic, so I knew it was going to happen. Okay, so what's happening here? Here I have a conducting rod. I have an external magnetic field. It has X's. What does that mean? It means into the page. Okay, so this V here basically means it's going this way. It's being forced this way. So what's going to happen is this is going to induce a current that creates a magnetic force going this way. It's going to oppose that motion. Okay? So again, here we want induced current, so that is our electron flow, and so we are going to use our left hand. So again, we know the current, or sorry, not the current, we know that the magnetic field is going into the page, so our fingers here need to be into the page. We know that our magnetic force is this way, so our palm has to push to the right. And look at that. What is our thumb doing? It's going to the top of the page. So my electron flow here is going north or to the top of the page. And that's all we got to do. Okay? Want to try B without me? Just pause it. Just pause it. You can do it. Just try to figure it out. Okay, you got it? So let's do this one. Again, we see the V here. I know it's weird. It should say like applied force or something like that, but it just means that it's moving that way. It has a velocity that way. So again, we need to oppose that motion, and we need to create a magnetic force this way, or at least the rod is going to create an induced current that will have a magnetic force that goes to the left in this situation. Okay, so what's going to happen? Again, we're using our left hand because we care about induced electron current. So my magnetic field's going into the page. That's what the X's mean. My force is going, you probably can't even see that. You just see my arm. Oh my goodness. So the force is going, of course, to the left. Try to do that. Is that any better? No, you can probably just still see my arm. The force is going to the left, so our palm has to be faced to the left right there, okay? And so what ends up happening there is my thumb is facing downwards when I arrange my hand in that kind of situation, okay? So that is what's happening. So my electrons are going to be going to the bottom of the page or south. And then since this is connected to these other conductors, you do have to consider the fact that this is now making a circuit where the electrons are now moving all around the circuit. So they're actually going to be going upwards through the resistor. Not upwards, sorry, northwards through the resistor. That's what that R is. You don't need to know what a resistor is. You did learn in Science 9, but that's okay. And so that is what's happening. So it's important in something like this that you note that, oh, this is creating an entire circuit. Why is that important? Well, that's basically how we do everything these days. This is how a lot of our electricity gets figured out. And this is how a lot of things happen, because when you have something like this, then you actually have a circuit. So you move it this way, creates a circuit one way, you move it back the other way, the circuit goes back the other way, and it just kind of keeps going back and forth, which again, that alternating current is far more efficient than just a direct current going one way the whole time. Okay, there you guys go. That is electromagnetic induction. That is how we can create electric field using a magnetic field. So again, in this case, it has to be moving. One of them has to be moving in relation to the other, and then we have an induced electric field due to a magnetic field, which is pretty amazing, okay? So if you haven't gotten it by now, electric fields, magnetic fields, they are really, really tightly knit together. Okay, they are very related with each other. And you know what? We're not even done, because then when we get into electromagnetic radiation, just listen to the name of it, electromagnetic radiation. So this is really just like the basis for so much in our world here. And it's really, really important. But that's it. Okay, I do have one more lesson for you guys going over some motors and stuff like that, but we'll leave that until later. This requires your significant attention for now, okay? So good luck.